Okay. So no quiz. All right. So we're talking about emission spectroscopy. This is, have you seen this instrument in the corner of the room?
That's why it doesn't work.
All right. Well, no, it works very well. In fact, it is the most, in my opinion, is the most sensitive instrument we have. In fact, it's arguably the most sensitive instrument, spectroscopic instrument on the planet, spectral fluorometry. But it's for a very narrow group of molecules, and well, yeah, I can tell you why. In an absorbance spectrum, what's the background? Do you ever think about that? What's the back? Yeah, everything isn't what you're looking at, right? So isn't the background kind of bright? Right? Because yes, it's an incident intensity. But in fluorescence, what's the background? Yeah, there's nothing. So you can work your PMT to the max and with fluorescence spectroscopy. That's why it's so extremely sensitive. And it works. The problem is there's two buttons on, and this is actually the same machine we have. Maybe they fixed it by now, the mode of turning it on. If you turn it on in the wrong order, you see a little puff of smoke in the back. And the only reason I know that is because I witnessed it. No, I didn't do it. It's very clear how to turn what on first and what on second. But if you don't follow the rules, you see a little puff of smoke. Then it's like $3,000 to replace the lamp. So it works. It's just sitting there. What we're leaving it for now is just pretty much for research, like that Scorpion. The last time it was used was that Scorpion project. Try to quantify and identify the compound that fluoresces in scorpion shells. Okay, so we talked about this is an equation for what? What process? What's the process? Energy is not a process. Oh, I think the process for getting an excited state. I was thinking more of the A word, absorption, right? Did you? Speak up, Alice. Okay. So, here, this is a diagram of what type of process? Emission. Or the other way, you're thinking return to ground state, right? Okay. So we talked about, here's the light coming from a continuous or a discontinuous light source. Discontinuous, right? And how you can pick a line, and they're so narrow that they rarely overlap, but they sometimes do. And this is where we left off. Just what happens to that energy, right? A molecule absorbs energy. And this diagram tries to explain what's going to happen to that energy. The energy has to what? It has to transfer. Everything wants to get to its lowest state, right? And in spectroscopic terms, its lowest state is ground state. So dissipate might be a good way to think about this whole diagram. Dissipate. Pablo, what's dissipate? What does that mean to you? You want to help them out?
Disperse.
Exactly. Disperse, right? Except dissipate kind of, to me, it has a little connotation of spreading things out, disperse, but in a way that just everything decreases, right? And that's all this is. How does the absorbed energy dissipate, right? Okay. How does it spread around? How does it, right? That's the natural way of doing things. So see if we can make sense out of this diagram. Okay. Let's start with, I don't know, Sir Rico. How about this talk? Now, just exactly what a singlet and a triplet state is, I think we'll leave that for Robert to explain. No, we haven't even had that in PChem yet, have we?
S1, S2.
All right. Yeah, there you go. That big S's are singlet state, and T are triplet state. Okay. Really, all it really is angular momentum. Can a state jump? Now, we're so used to thinking of linear momentum, right? Like if I throw a baseball to Anna, right? She can catch it and her hand keeps moving a little bit. That's a successful transition, right? But angular momentum, that's like this spinning bike wheel, right? So if I want to transfer this angular momentum to Anna, right, it needs to be some successful, nice, smooth transition. But angular momentum, what if she's oriented in a funky, weird way that it just can't transmit? It's just energetically impossible. Because you remember that bike wheel? You almost have to have held it and realize, dang, it's really hard to twist. And then if you get microscopic, there's only certain positions it can be at, right? Oh, that was P-Chem. Oh, we should have brought that in. Anyway, okay, getting way too deep anyway for this class. The point is that there's certain, it's just not energetically, it's just not going to work out. Okay, it's just they're not going to, you can't convert from that type of energy to another, okay, to that type. But look at the darn thing, it's happening. Might as well start with that one. The S and the T's are the singlet and triplet, right? That little F, it's happening. You can go, it's supposed to be impossible, right? But it's happening. Okay. Yeah. Well, little c, you're going from singlet to singlet. It's like catching the baseball, the momentum's transferred nice and smooth. But F, it's not supposed to happen. But it does. Okay, so let's get some names on this stuff. I think we already did absorption, didn't we? Alice, what was absorption? It was B as in boy, right? Okay, absorption. And all the little absorption lines were starting from where? Yeah, but in the ground state, didn't that... How come there's so many lines in the ground state? Adriana, what's going on there? Look at all those lines. I'm talking about, look at all these guys. Look at them all. How come there's so many lines? Ground state, there should be one line, shouldn't there?
Is it like the rotational?
Okay, we're getting there. The ground state is there's electronic states, and there's vibrational states, and there's rotational states, and then even in between those rotational states are nuclear spin state. I mean, it just gets tiny, narrower, narrower, narrower. Electronic state transitions involve what type of light? Just a little review here. You're changing the electronic distribution around a molecule. It's high energy stuff. You're going from this type of electronic distribution to this one. U, ultraviolet, or, there's the V, visible. Okay? And then you want to jump in, okay, smaller energy transition, just vibrational modes of molecules. That's infrared. And then you go to rotational. Yeah, it's infrared too, and microwave, right? Especially microwave, because you know what works on the microwave. What's spinning? Water, right? Generate heat. Okay, there's a good one to lead off. Could you follow that? Could you follow? You remember that story about microwaves absorb what type of radiation? Sorry, water absorbs what type of radiation? Microwaves, which is lower energy than infrared. Okay, you with me so far? Okay, so this water molecule absorbs some microwaves. It starts doing what? Even faster. Not vibrates. Microwave, it's too low of energy. It's rotating, spinning. Okay. There's a word for why it heats up the hot dog. You have a bunch of water in that hot dog. The water friction, yeah. All right, but friction's not one of our choices. But it's the right type of thinking. Okay. It's this spinning water molecule slamming into all the other stuff around it, generating all this heat. But now, we can't be. We're not supposed to be talking about. We're not supposed to be talking about rotational relaxation. We're supposed to be talking about vibrational relaxation. These molecules, they're vibrating, they collide with other molecules around them, and they just kind of dissipate their energy that way. So wherever you see vibrational relaxation, which is little a, all right, it's losing its energy. Okay, So whether you're in the ground state or an excited state, you can, this vibrational relaxation happens. Okay, that's little a. Okay, so if that's little a, how about, let's compare D and G. Or we can keep going here. Oh, let's before we do that, we've done singlet, we've done triplet, we've done absorption, right? Okay. How about, and we did vibrational relaxation, that was A. Let's go back to C here. Okay. C is kind of similar to vibrational relaxation. It's just another way of dissipating, energy. But notice how you get an A, you get vibrational relaxation. It hits the electronic state, right? It can't, relax anymore through vibrational relaxation. But this vibrational energy really lines up, has the same energy as this lowest electronic state. So it just kind of crosses over. Well, no, they call it internal conversion. Yeah, because you're still in singlet. So it's internal. I mean, you're still in a singlet state. So it's very easy for it to happen. I mean, it's the linear momentum idea, catching the baseball, energy transfer is nice and smooth, right? So that's internal conversion. So now then it can go back to doing its vibrational relaxation thing. Pretty much just everything just warms up. It's just generating heat. So that's friction idea, right? Everything's colliding with everything else. So everything's honky-dory, honky-dory. Okay. Now, so let's cross internal conversion off. I don't want to. Okay. Now the inter-system crossing, notice how it's the same idea, right? But it doesn't happen very often at all. Okay, and it's rare, but it happens. Okay, it can do it. It just lines up, go to a triplet state. Okay, there's kind of a special situation for that to happen, and we'll talk about that. What else? Okay, let's cross off. So intersystem crossing, we said was F. Okay, now how about, D and G? Okay. Yeah, we have to pick, they're going down. You have the words fluorescence and phosphorescence I'm hearing, right? Okay, which one is which? Okay. Now, the glow-in-the-dark toys. I think is everyone on the same page that these guys, this is emitting light, right? So everything we've been talking about so far is radiation-less decay. No light's being emitted. But now when you start using the word fluorescence or phosphorescence, light's being emitted to dissipate energy. So, the only, do you remember writing these words down? So this is the definition. Fluorescence happens on the nanosecond time scale, right? That if this was fluorescence, these glow-in-the-dark dinosaurs, I'd shine my light on it, take it away, and in about a nanosecond, the light's emitted and it's done. It's called the lifetime. If I shine a light on it, and then, look, I got kind of bright. You see that? Get his head going. All right. Okay. Now, if the lifetime's on the order of milliseconds, like 1,000 times longer, or even more, 10,000, the lifetime, it lasts longer. Okay. It's hard for you to tell, but which one is this? Is glow-in-the-dark toys an example of phosphorescence or fluorescence? Fluorescence happens way too fast. You wouldn't even be able to see it. Phosphorescence. So a millisecond, it also sounds really fast, but it's really, really slow in comparison to. It allows us to see it, right? And remember, lifetime is just the time for half of it to dissipate. So, and your eyes are so sensitive that you can see this guy for several minutes, right? So phosphorescence is the one that lasts a really long time. Okay, now let's take a look at this. You're going from D and G. We're trying to figure out which one is which. One happens really fast, one happens really slow. In a chemical world, really slow. You have singlet to singlet. Allowed transition, nice smooth transfer of energy. You have triplet to singlet. Not allowed transition. It's not supposed to happen. Which one would be which? Triplet to singlet has to take longer. So that one is the phosphorescence. So G would be phosphorescence. D would be fluorescence. All right. Okay, what did we miss? Hmm? That's a good question. Okay. Now, probably history-wise, did we cover them all? We didn't. Oh, internal, external conversion. Okay, internal, external conversion. There's only one left. By deduction, it's got to be. Oh no, we ran out of words. It's C. It's C. C is internal, external conversion. I know, it's all the same thing, really. Right? I think the idea is see, you're converting energy from one state to another, and they're kind of running out of words, I guess. I think external conversion is more like everything's got to be contained in something. I'm thinking of the size of the container, maybe, right? But it fits the definition of internal conversion because you're going from one state to another state. Okay. But it's radiationless, so it's about as much light as I can shed on that. Huh? Get it? Okay. Now there's some general ideas. Let's say you have a molecule that's really floppy, right? Like an alkane chain or something. You have a molecule that's really floppy. He'd be really good at what? Right? Because he can absorb. Okay. I'm trying to see if you can picture how. See this vibrational relaxation? He can lose his energy really easily by just flopping around, hitting other stuff. Okay. So this type of molecule is at one extreme. The other extreme is a very rigid, stiff molecules. Aromatic stuff. Aromatic stuff. All right? Not floppy at all is the other extreme, is how I picture this stuff. So the floppy stuff, really good at vibrational relaxation, this whole internal, external conversion thing. Okay? Really rigid stuff, not so much. Right? So what's going to occur? How is it? These kinds of molecules might reach the ground state how then? Right? Because you can do this whole vibrational relaxation thing, or you could D and G. Fluoresce or phosphorus. So I was saying how, that spectrophotometer is the most sensitive instrument on the planet. Well, it only works for a very narrow category of compounds. And those compounds have to be extremely rigid, aromatic. So yeah, a lot of that stuff is toxic. Okay. Okay. Sketch a general absorption spectrum and a plausible corresponding emission spectrum. Okay. What would be your axes for an absorbance spectrum? Yeah, why not, right? Did you hear what Rob said? Absorbance? Ah. Right? And then now, do I draw lines here, or what? Remember drawing your UV Viz people? You've all done this by now, right? It's a big blob, these absorbance spectra, right? Okay. emission spectrum. What does an emission spectrum look like? Now this is going to be hard because you haven't used. I don't let you touch that machine.
What is the opposite of the absorber?
Ooh, now we're starting to think though, right? Because it has to absorb to emit, right? So very often they're kind of reflective, but there's several different types of emission spectra, so we'll talk about it. But it needs to be at a lower. Well, yeah, it's very reflective. It's a blob too, but you could kind of draw it.
As soon as you're hiding, finish the sentence. You're killing me.
Yeah. Yes, it doesn't have to be the same thing, right? But the wavelength. Oh, what would be this? What would be the y-axis?
Signal?
Yeah, intensity. Because remember, there is no background. You're just measuring light intensity. Okay, that collected light intensity, and the wavelength will be shifted very often. Red shifted. What does red shifted mean? All right. That means you take your absorbance spectrum and just shift it towards the blue or towards the red? Towards the red. Is that a higher energy or lower energy? Lower energy. Right? So pretty much just take it and shift it towards the red. And that would be your emission spectrum. Okay. What is the purpose of a spectrofluorometer? Probably to do what? Kathleen, you'd say what? What's the purpose of a spectrofluorometer? To get a what spectrum?
Pain spectrum.
To get a emission spectrum. Yeah, that's its goal, to get an emission spectrum. Label its major components. Okay.
Is that another amount of
So Emily, can you label some of these components for us? Oh yeah, we're not supposed to say sample selector. You mean wavelength selector, and we're supposed to use the word what, Sandy? Monochromator, right? Okay, so we have.
I see a lot of diagrams.
How many monochromators do you see?
just one.
Careful.
But
Look at what's going on here.
oh, okay.
Let's back up and look at the arrows. Why are there so many different colors coming from the light bulb?
It's white light.
Roy G. Biv. Okay, it's going to a box, which we're not supposed to say box, we're supposed to say what? Monochromator. And what's coming out of the monochromator?
Blue.
How many wavelengths?
Uno. One.
One wavelength, right? Striking something. Look what's coming out of it.
Green.
Why did I choose blue and then these reddish colors?
Different intensities.
The opposites on the color.
Yeah.
Yeah.
You have a color wheel. It's really
So
intense.
This isn't.
Everything that's not blue.
We're not. You're on the right track if we were talking about absorbance spectra, but this is light coming from. What is this thing right here?
Mirror. Prism.
He must be the what?
Gypsy magic.
Somewhere you got to put what you're interested in analyzing.
Oh, sample.
That's your sample, right? There's blue light is striking it.
Okay.
Is one type of wavelength coming from it?
No.
No, several are,
And
right?
then you have another monochromator after this.
So hang on. Why are these guys
Yes.
why did I pick these colors here and I picked blue to strike it? What's the difference?
More diluted.
What's the difference between these in energy?
The red is lower in energy.
Red is lower in energy, right? That fits the idea of this whole emission spectrum, right? It's going to absorb something, but it emits red-shifted energy, right? Okay. Do you see why? See, look at this. It's going to absorb. It's going to absorb. Here's your emission, right? Jumping from down to here, or phosphorescence, if that's you want that one. But it absorbs always a higher energy because you get vibrational relaxation before it goes down. So it's always absorbing a higher energy than what's emitted. Notice that? It's always absorbing a higher energy than what's emitted. So it will always be redshifted. And then what it emits, is it going to emit just a single wavelength? No. Unless it's an atom, right? We saw some atomic spectroscopy. Yeah, they're very narrow wavelengths. So this must be, a molecule sample in there, something aromatic. Okay. How did I know to pick blue? I had to take a what spectrum first? Absorbance. And see what wavelengths it absorbs. Makes sense? So it must absorb blue. So that's why I set this first monochromator to blue. Okay. And then it's striking another monochromator. And this monochromator is just set to red. And then the very final box must be a detector. Probably what type of detector, Ricky? What would you call it?
Oh, man. A good one. Diode,
3 letters.
I don't know.
3 letters.
What
Only.
is it, Dad?
Yeah, Dad. That's close. Wrong 3 letters.
Fat?
You want to help him?
Mom? Tid.
Has dinodes. Has a dark current.
Wait, diodes and a
Dinodes.
Oh, diodes.
One
Dark
day
current.
with the, you gotta make it really
Has a
cold.
dark current.
DNA does not
Isn't that
exist.
thing?
Someone said it? Someone started? Emily?
What the hell was that thing?
You're Andy. What is it? Help these poor people.
Oh, my God.
Dark
Oh, yeah.
PMT, photomultiplier tube. Exactly.
There we go.
Okay.
That's a type of detector?
Very, very often because it's extremely sensitive. Because
Dark current.
right? Because think about PMT is perfect for fluorescence because if it detects a photon, it's going to send off right? There's no background. PMTs are perfect for spectral fluorometers. Okay. Okay. What's the difference between an emission and an excitation spectrum? Okay.
So is that a second monochromator there, like Rod said? Or?
Yep.
Yeah.
And then a PMT.
Okay.
So,
So any questions on the components? We're good?
so we don't have a detector that can handle
It's
more
definitely
than
gonna
one
be
wave? Is that why we have to have a second
That-
monochromator?
Because yeah, you're right. You could. Now they do. Instead of having,
Is that just
okay, think about this. Think about this. You could, instead of having a PMT here, you could have a DAD. And Ricky said a DAD. Diode stands for diode array detector. So you have a little. Remember what that is, right? Which one's more sensitive?
I don't know.
A DAD or a PMT?
I'm guessing the
PMT is so much more sensitive. In fact, when I was, these machines, these spectral fluorometers, they're made with both a DAD and a PMT. And and both of them came upstairs to try to sell us the machine. Okay. First came the one with the DAD. That's made by Perkin-Elmer, and had the little cuvette, put the sample in there, and we got this nice, beautiful spectrum, and it was cheaper too because we don't need this second monochromator, right? Okay, but then I just dumped out everything that was in the cuvette. It was quinine. Quinine is in if you go tonic water, right?
Makes you flow.
And yeah, so if you take quinine and that would be a good demonstration in this room, right? You can actually get it to look a little blue.
You drink it?
But
I don't want to drink that.
that was it was on some research project poster. Okay, so anyway, I dumped out everything that was in the little cuvette, just filled it up with water, put it back in the machine. He says, "Oh, there's no way you can see that." I said, "Well, let's just try it, because I want to see how sensitive." Because I know how the potential of these machines, theoretically. So I dumped it all out, filled it up with water, put it back in the cuvette. No way you can see that. No way you can see that. So, and he was right. You can't see it. The other guy comes with the PMT. Okay, same sample. I want to test both on samples, right? So same idea. I had the cuvette. Oh, nice, beautiful signal. I dump out everything in the cuvette, put it back in. Oh, you're not going to be able to see that. Huge signal. I dump it out again, fill it up. You know, because there's always some left on the sides. You can see it. I did that like 3 or 4 times. This thing is extremely. I knew it should work because you can see it in the tonic water, right? If your eye can see it, PMT is more sensitive than your eye. Diode ray detector, right? Because it's dispersing all the colors. It's not making use of that all the technology of a photomultiplier tube. Okay, anyway, yeah, good question. I think because also how did to answer Alice's question? My view is what's the most difficult major on the planet? Chemistry, right? How many chemistry majors are there?
We got it.
Not very many, right? So the guy selling the stuff, was he a chemistry major? Did he have, right?
No, he's a business major.
But you couldn't even do that.
Or the other B major, right? It's just don't have the lab, don't have the foundations for chemical analyses. Okay. All right. Okay. Emission and an excitation spectrum. So let's take a closer look at this machine here. Here's our machine.
From any other class.
So emission spectrum. Emission spectrum with that. So there's 2 types of spectra you can get with a spectral fluorometer. One is an emission spectrum, the other one's an excitation spectrum. Excitation spectrum essentially is an absorbance spectrum. It's the exact same thing. Because what you do is you set you find where it fluoresces, where does it give off light, and you pretty much just set your emission monochromator to it. Now this is called just put some words on there. So there's 2 monochromators. They call this the emission monochromator. Okay. So in an emission spectrum, let's just emission monochromator. And the excitation. Let's see what these guys are doing. Excitation. Okay. So if you're going to do an emission spectrum, right? You set and scan. So you set your emission monochromator to 1 wavelength. Set the wavelength. You put a little lambda there. Okay. And you scan the wavelength on the excitation. So if it absorbs, it'll emit, right? So you'd only get a signal when this guy's actually absorbing light. So it's the same as, it's going to look exactly the same as an absorbance spectrum.
So is the other monochromator the excitation monochromator?
Yeah. Yeah, let's label him. He's the excitation monochromator. Okay. Now the other, if you want to get the excitation spectrum, it's just the other way around. Scan this guy, set this guy. Okay. So right? Oh, did I screw this around here? Emission monochromator. Oh, I got them flipped. I have them flipped. Sorry. Sorry. I have them flipped.
What does it say? Set and what?
Set wavelength, scan wavelength.
Scan.
Okay. I had them flipped. For an emission spectrum, right? You can see what we did up here? We set the wavelength, and then we scan this guy, and we'll get a whole bunch. We'll get this spectrum we did up here. So emission spectrum, it's when you just pick a wavelength where it absorbs that, and then you just get the whole big, see what light it emits, scan the emission monochromator. If you want to get an absorbance spectrum, better known as an excitation spectrum if you're using a fluorometer. It's just the other way around. Okay. Okay. So then you set the emission monochromator to single wavelength, and you just scan him, see where he absorbs.
So
Yeah.
your emission and your excitation monochromators basically switch places.
But don't switch places, you just change what they're doing. Right? Because those little gratings rotate. And you can,
Oh, so you can get an absorption spectrum and an emission?
yeah, you can get both. So it's kind of a cheaper machine. You don't have to buy a UV vis. But the dang thing has to fluoresce. So if it doesn't fluoresce, you're not going to get absorbance spectra. So it's kind of narrow.
The excitation monochromator is also connected to the photomultiplier?
No, they're always in this order. The light has to go to the excitation monochromator because he's always determining the wavelengths that hit the sample. So the first monochromator is always called the excitation monochromator. And then the light emits. How do you scan it? The computer scans it. Right? The computer's going to scan the wavelengths that it selects to kick out of there. So if it's...
When you said scan, I think that's where your detector is.
Yeah.
Oh, sorry. No, scan means that little grating's moving. Right?
Hey, have you used any of these? It's scary noises.
Okay. Oh, sorry. Here it was right here. Okay. Emission occurs in all directions. I don't know if we noticed, but this is at 90 degrees. Right? They collect the emission at 90 degrees. And that's simply because you get scattering everywhere. Right? So you get the least, you can't avoid scattering, but you get the least scattered radiation. Because you want emitted radiation, not scattered light, not the excited light being scattered. So it's just, you get the least scattered radiation that way.
If it's at 90 degrees?
Yeah, if it's at 90 degrees. That's why they're all built that way. And what do we say, what characteristics make a great emitter of light for a molecule? Very what? Not very what?
Rigid and
Very rigid. In fact, what type of molecule? Starts with an A?
aromatic.
Aromatic. Okay. And then I have one more thing here. Let's see if it works.
So very rigid.
Okay, so any questions before I do our little movie?
So very rigid. I know, but it's great for not.
Yeah, because if it's really floppy, it's going to dissipate all its energy just by vibrating, vibrational relaxation. It's not going to emit or fluoresce.
Yes.
Yeah. And notice how this is percentage stuff. I mean, if you have a molecule that's really rigid, he's not going to 100% of the time emit light. He's going to do a lot of vibrational relaxation too. It's just that he will emit light. He doesn't have to emit much to detect it, right? It could be 1 out of every 10,000 events or something. They call it quantum yield, but okay. No, I saw this morning and I haven't really played it. I mean, I went through it really fast. Let's see what it does here, because it looks like a little animation. Notice how the ground state, excited state, right? Notice how you have a ground state. All these states are what? Singlet states. So I think it's going to show an absorbance event, right? And then do a little internal conversion, right, to the lower excited state. And then it can't fluoresce or phosphoresce because they're both singlet states. So it might do vibrational relaxation or internal conversion. Let's see what it does here. Oh, okay. Did you see that?
Yeah. There's an energy.
The only,
That way,
right? Do you see the words? That's what's the difference between, you had to be really fast to see it. What was the difference between internal conversion and external conversion? Yeah, what's the difference? So they're both dissipating energy, radiationless decay. Internal conversion was when the little vibrational levels line up, so it could transfer over and get a step down, line up, transfer, and maybe you can reach all the way back to the ground state. But here, they don't line up. The vibrational levels and electronic state, they don't line up. So it has to be external conversion. One more time. It's like 30 seconds, and then we'll let you go. And watch, see if you can watch the words as what's going on up here. Okay? Yeah, it's kind of trying to describe it. It happens fast, though. You ready? You see all that?
Yeah.
You don't want to watch it again, do you? All right. Have a good day.